Right now, 115 degrees of raw, unmitigated thermodynamic energy is rewriting the meteorological rulebook across the North American continent, setting the stage for a planetary-scale collision that researchers are watching with absolute fascination. We are not talking about a fleeting afternoon heat index artificially inflated by localized humidity levels. We are looking at verified raw kinetic air temperatures that push the absolute limits of what human infrastructure and biological systems can endure. It is an event that is currently triggering a cascade of secondary atmospheric anomalies, essentially transforming the United States into a real-time laboratory for extreme planetary physics. On one side of the continent, an inescapable thermal blockade is baking the Earth so severely that asphalt infrastructure is fundamentally degrading. Yet simultaneously, this exact same thermal mass is acting as the primary engine for a relentless, churning storm factory thousands of miles away. But here is the twist. While the public and the media remain entirely focused on the searing temperatures and the violent atmospheric clashes lighting up Doppler radar screens across the country, there is a third massive component to this sequence playing out in total silence. It is a dormant thermodynamic threat hiding in the Atlantic Ocean, quietly storing an unprecedented amount of energy, and it fundamentally alters how we must look at the remainder of this weather season. We are going to deconstruct the anatomy of this continental anomaly from the ground up. By the time we finish, you will understand exactly how the atmosphere operates as an interconnected fluid machine, why the coming days are so critical, and what the satellite data is telling us about the hidden dangers that most people will never see coming until the final moment. To understand the sheer magnitude of what is happening across the country, we have to pull back and look at this from an orbital perspective. When geostationary satellites scan the central United States right now, they are observing a massive, entrenched, high-pressure ridge, a sprawling geographic dome of subsiding air that is entirely dominating the regional climate. In atmospheric physics, this is known as an anticyclone, but you can think of it as an invisible, continent-sized anvil pressing down on the troposphere. When air sinks, it compresses, and when it compresses, it heats up dramatically due to adiabatic warming. This heavy sinking air physically prevents any cloud formation or convection from occurring beneath it, which means there is no shade, no rain, and absolutely no mechanism for the trapped thermal energy to escape into the upper atmosphere. The air simply cooks, pinned to the surface of the Earth. Currently, this massive high-pressure blockade is anchored directly over the central and southern plains, and it is showing zero indications of structural weakness. But how does a stagnant, motionless block of air generate enough kinetic energy to tear down a house? The answer lies in fluid dynamics. The Earth's atmosphere is constantly striving for thermal equilibrium. It despises an imbalance. When you place a stationary, superheated mass of high pressure in the middle of a continent, the surrounding atmosphere is forced to react violently. The jet stream, the high-altitude river of fast-moving air that steers our global weather, cannot simply punch through this dome. Instead, it is forced to divert, riding along the northern and eastern edges of the high-pressure system. This creates a volatile boundary layer, a jagged perimeter where the scorching, expanding air of the heat dome directly collides with the much cooler, faster-moving air of the jet stream. Meteorologists often refer to this perimeter as a ring of fire because it serves as a continuous ignition zone for severe weather. So while millions of people trapped beneath the center of the dome are enduring life-threatening heat, millions of others situated along its periphery are about to face an entirely different manifestation of that exact same thermal energy. The heat and the storms are not coincidental. They are two sides of the same thermodynamic coin, intrinsically linked by the fundamental laws of physics. Understanding this connection is the first step in decoding the complex threat matrix that is currently unfolding. The central reality of this event begins with the sheer, undeniable data recorded by ground stations across the plains. Across southern Kansas and northern Oklahoma, meteorological sensors are projecting actual high temperatures to crest near 115 degrees Fahrenheit. We have to pause and ground that number in reality, because 115 degrees is not merely an uncomfortable summer afternoon. It is a threshold where the physical world begins to behave differently. At these extreme temperatures, the specific heat capacity of concrete and asphalt is overwhelmed, causing roadways to buckle and warp under thermal expansion. Power grids, burdened by millions of air conditioning units running at maximum capacity, edge dangerously close to cascading failure as transmission lines physically sag from the heat. The human body, which relies on the evaporation of sweat to regulate its core temperature, finds itself entirely outmatched. Within just a few minutes of exposure, biological heat stress can escalate into critical hyperthermia. Furthermore, this is not an isolated, single-day spike. The true danger of this particular atmospheric setup is its longevity and its geographical expansion. As the weekend progresses, the thermal boundary is actively migrating northward, enveloping South Dakota and Nebraska in temperatures well exceeding the century mark. Regions that typically experience highly temperate late summer conditions are suddenly facing an influx of triple-digit heat that their local infrastructure is simply not designed to handle. St. Louis is staring down a forecast of 101 degrees, while central Kansas faces sustained daily highs of 112. However, the most insidious aspect of this phenomenon occurs long after the sun goes down. A healthy diurnal cycle relies on nighttime radiative cooling, where the surface of the Earth releases the day's accumulated heat back into space. But beneath this specific high-pressure dome, that cooling process is fundamentally blocked. The boundary layer fails to decouple, resulting in nighttime temperatures that hover in the dangerous upper 80s and low 90s. When the environment fails to cool at night, human physiology is denied its necessary recovery period. The cumulative strain compounds day after day, turning a weather event into a slow-moving public health emergency. This leads us to a highly sobering statistical fact. Despite the visceral terror associated with violent storms, extreme heat consistently ranks as the #1 weather-related cause of mortality in the United States, outpacing floods, hurricanes, and tornadoes combined. The data is unequivocal on this point. Heat is a silent, invisible force that systematically overwhelms the unprepared, which is precisely why meteorologists treat a sustained 115-degree forecast with the exact same urgency as a landfalling hurricane. The human brain is notoriously terrible at comprehending threats that it cannot visually quantify. If you see a massive rotating wall cloud bearing down on your city, your evolutionary survival instincts instantly trigger an adrenaline response. The danger is concrete, localized, and highly visible. But a heat dome operates on a scale so vast that it completely defies our intuitive understanding of danger. Try to visualize the sheer volume of the atmosphere involved in this current event. We are looking at millions of cubic miles of superheated gas stretching from the surface of the plains all the way up into the lower stratosphere, completely dominating a landmass the size of Western Europe. There is no physical structure you can point to, no cinematic funnel cloud to record on a smartphone. There is only a crushing, omnipresent stagnation. To truly understand what is happening, we have to look away from Earth for a moment and consider the mechanics of planetary atmospheres elsewhere in the solar system. Think of the conditions on Venus, where a thick, impenetrable atmosphere traps solar radiation in a runaway greenhouse effect, preventing any thermal release. While Earth is entirely different, the fundamental physics of a high-pressure heat dome mimic this trapping mechanism on a localized, temporary scale. The high pressure acts as a physical barrier, deflecting any cooler air masses that attempt to penetrate the region. Because this threat is entirely invisible, human intuition frequently miscalculates the risk. People assume that because they have survived hot days before, they can simply endure this one through sheer willpower, but biological limits are not governed by willpower. They are governed by thermodynamics. If you enter a vehicle parked in 115-degree ambient heat, the interior cabin temperature can surge past 150 degrees in a matter of minutes due to the greenhouse effect of the glass windows. At that temperature, cellular proteins begin to denature. It is a mathematically guaranteed biological failure. Yet because the sky is clear and the sun is shining, the environment projects a false sense of security. This cognitive dissonance, the gap between the serene appearance of a sunny day and the lethal reality of the thermal environment, is exactly what makes this atmospheric pattern so uniquely dangerous. We are fighting millions of years of evolutionary programming that tells us to only fear what we can see, while the most statistically deadly force in the atmosphere surrounds us in broad daylight, entirely unseen. While the center of the country bakes in silence, the northern edge of this thermal dome is about to become one of the most violent environments on the planet. To understand why, we have to examine the precise mechanism of convective initiation. Remember that the atmosphere is a fluid, and like any fluid, it seeks balance. Right now, the jet stream is carving a path from the northwest, dragging cooler, highly energized air along the northern boundary of the stagnant heat dome. This collision zone, stretching across Iowa, Minnesota, Wisconsin, and Michigan, is where the thermodynamics become incredibly hostile. The superheated air at the surface is desperately trying to rise. It is packed with thermal kinetic energy, making it incredibly buoyant. However, it is momentarily capped by the high pressure. When an incoming disturbance from the jet stream finally provides enough lift to break that cap, the result is explosive. It is the atmospheric equivalent of detonating a controlled demolition. The hot surface air accelerates upward into the freezing upper troposphere at speeds that can exceed 100 miles per hour, creating massive, towering cumulonimbus clouds that reach altitudes of 50,000 feet. This violent vertical motion is the engine of a severe thunderstorm. As the storm matures, it begins to unleash its stored energy in two primary forms. The first is straight-line winds. When the massive column of rising air eventually cools and condenses, it becomes heavy and plummets back toward the earth. This downdraft hits the ground and violently spreads outward, generating straight-line wind gusts that can snap utility poles, flip large vehicles, and cause structural damage akin to a low-end tornado. The second major threat is large hail. Inside these towering storm clouds, the sheer force of the updraft is so powerful that it intercepts falling water droplets and forcefully throws them back up above the freezing level. The droplets freeze, fall slightly, collect more moisture, and are thrown upward again, accumulating layers of ice like the rings of a tree. It is only when these chunks of ice reach the size of golf balls or larger that they finally become too heavy for the updraft to support, crashing to the ground with devastating velocity. This cycle of explosive updrafts and crushing downdrafts is currently repeating itself in wave after wave across the upper Midwest. It is a relentless, mechanically efficient storm factory powered entirely by the heat dome anchored to the south, proving that in a closed planetary system, massive heat anomalies never stay isolated. The energy always finds a violent way out. Now, here is where the situation escalates from a standard summer weather pattern into something much more alarming. Meteorologists are hyper-focused on the atmospheric parameters aligning for Sunday because the data suggests the potential for a severe weather outbreak that operates on an entirely different level of structural organization. Up until this point, we have discussed standard thunderstorms fueled by heat and vertical updrafts. But on Sunday, a critical new ingredient is being introduced to the upper Midwest: extreme directional wind shear. Wind shear occurs when the wind changes speed and direction at different altitudes. By Sunday afternoon, the forecast models indicate that the low-level winds near the surface will be surging aggressively from the south, pulling in massive amounts of rich, humid moisture from the Gulf of Mexico. Simultaneously, the high-altitude winds of the jet stream will be roaring out of the west. When you have lower winds pushing north and upper winds pushing east, it imparts a twisting motion to the atmosphere. It creates an invisible, horizontal rolling cylinder of air. When one of those explosive thunderstorm updrafts interacts with this rolling cylinder, it tilts it vertically. The entire storm begins to rotate. This is the precise genesis of a supercell, the most highly organized, dangerous, and long-lived classification of thunderstorm on Earth. A supercell contains a deep, persistently rotating updraft known as a mesocyclone, which allows it to sustain itself for hours and produce massive hail and violent tornadoes. The atmospheric fuel available for these storms on Sunday is staggering, reaching parameters that routinely trigger high-end alert levels among forecasting agencies. But here is the most concerning aspect of Sunday's structural setup. As these discrete supercells mature throughout the late afternoon across Minnesota and Iowa, the atmospheric dynamics suggest they will eventually merge into a sprawling, forward-propagating line of immense thunderstorms. This cohesive wall of violent weather is projected to march aggressively eastward, targeting major population centers like Milwaukee, Grand Rapids, and potentially Detroit. The timing of this advance is what makes it so uniquely dangerous, because this complex is expected to push through these regions overnight, long after the sun has set. Nocturnal severe weather represents a terrifying paradigm shift. During the day, you have a visual confirmation of the threat, you can see the sky darken, you can spot the lowering of a wall cloud, and you can physically verify the danger. At 2 in the morning, plunged into total darkness, stripped of all visual cues, your only lifeline is the digital alert on your phone or the shriek of a weather radio. If you sleep through that alert, you are left entirely defenseless against a highly organized atmospheric weapon that was forged hours earlier by the heat dome 1,000 miles away. With any forecast this extreme, we must apply rigorous scientific skepticism. It is very easy to look at the maximum potential of an atmospheric setup and immediately project a doomsday scenario, but planetary physics is rarely that linear. The atmosphere is a chaotic, nonlinear fluid system, and predicting its exact behavior requires navigating immense variables. While the thermodynamic fuel available for Sunday's supercell threat is undeniably astronomical, the actual initiation of those storms is not a guaranteed certainty. There is a specific meteorological phenomenon known as a capping inversion that could dramatically alter the outcome. Earlier we discussed how high pressure acts like a lid. Well, an inversion is a layer of unusually warm air situated a few thousand feet above the ground. In order for thunderstorms to form, the hot, moist air at the surface must be buoyant enough to punch through this warm layer and reach the freezing altitudes above. If the inversion layer, the cap, proves to be too strong, it will simply suppress the rising air. The surface will become incredibly hot and humid, the energy will build to astronomical levels, but the storms will fundamentally fail to fire. It is the atmospheric equivalent of a loaded spring that never gets released. Furthermore, global weather models, such as the American GFS and the European ECMWF, often display subtle disagreements regarding the precise timing of the jet stream trough that provides the necessary lift. A discrepancy of just 50 miles in the placement of the frontal boundary, or a delay of just 3 hours in the arrival of the upper level forcing, can mean the difference between a historic tornado outbreak and a completely quiet, sweltering afternoon. Meteorologists are extremely careful to emphasize that Sunday represents a high ceiling environment, meaning the worst-case scenario is structurally possible, but it requires the exact, flawless synchronization of every single atmospheric ingredient. If one component is slightly out of phase, the entire storm engine stutters. This is the inherent challenge of advanced forecasting. We possess the satellite technology and the supercomputing power to identify the precise ingredients for a disaster days in advance, but the ultimate trigger remains governed by the microscopic chaotic fluid dynamics of the atmosphere, reminding us that we can observe planetary mechanics, but we cannot fully command them. While the severity of Sunday's storms hinges on highly sensitive atmospheric triggers, there is one aspect of this current global pattern that is absolutely undisputed, mathematically verified, and deeply concerning. We must shift our focus away from the continental United States and look out into the vast expanse of the Atlantic Ocean. Right now, the tropical Atlantic is eerily, unnaturally quiet. During a typical August, this ocean basin is a churning conveyor belt of tropical waves marching off the coast of Africa, organizing into depressions and threatening to develop into massive cyclones. But currently, the satellite feeds show a barren landscape. The mechanism responsible for this suppression is a robust El Niño phase situated in the Pacific Ocean. El Niño alters the global Walker circulation, sending relentless high-altitude wind shear ripping across the Atlantic basin. This shear acts like a massive atmospheric scythe. Every time a cluster of thunderstorms attempts to stack vertically and organize into a hurricane, the shear forcefully decapitates the system, tearing the thunderstorms apart before a low-pressure center can consolidate. On the surface, this suppression appears to be incredibly fortunate, but here is the concrete, irrefutable danger. The Atlantic Ocean is essentially a massive planetary heat sink. All summer long, it has been absorbing an unfathomable amount of solar radiation. Normally, hurricanes act as the Earth's natural cooling mechanism. They extract that thermal energy from the ocean surface and vent it high into the upper atmosphere. Because the wind shear has completely prevented any storms from forming, that thermal extraction process has not occurred. The ocean has become a fully charged thermal battery. Current measurements of ocean heat content, a metric that tracks the depth and intensity of warm water, are reading at historically anomalous levels. The water is holding a staggering payload of potential kinetic energy, simply waiting for an ignition source. This is not a speculative model or a chaotic forecast. It is a direct thermodynamic measurement. The energy is physically present, trapped in the upper layers of the ocean, artificially restrained by a temporary atmospheric wind pattern, and accumulating more power with every passing day of the summer sun. As we map out the timeline for the next several weeks, the transition of these planetary systems guarantees extreme volatility. The massive heat dome currently suffocating the plains cannot defy the changing of the seasons indefinitely. Eventually, the structural integrity of the high-pressure ridge will fracture, allowing a deep, aggressive cold front to plunge southward from Canada. When this occurs, the temperature whiplash will be historically severe. Regions that are currently enduring 115-degree heat indexes could see their ambient temperatures violently crash by 40 to 50 degrees in a matter of hours. For agricultural sectors in the far northern reaches, such as northern Minnesota, the models suggest this thermal crash could drive nighttime temperatures perilously close to the freezing mark, introducing a sudden immense stress factor to unharvested crops. Simultaneously, the southwestern United States will continue to experience the localized effects of the monsoon, where intense, localized diurnal heating triggers rapid flash flooding across the arid landscapes of Arizona and New Mexico. But the most critical focal point for the future remains the heavily loaded thermal battery in the Atlantic. Historical atmospheric data provides a grim warning for this exact scenario. As we transition into September and October, the global wind patterns typically begin to shift, and the intense El Niño wind shear that has been protecting the basin often naturally relaxes. If that shear drops, even for a window of just 4 or 5 days, the atmospheric scythe is removed. Any minor tropical disturbance that wanders over that superheated ocean water will suddenly have unrestricted access to a pristine, low-shear environment and an endless reservoir of high-octane thermal fuel. Under those specific conditions, the laws of thermodynamics dictate rapid intensification. We have seen this play out in recent history, where a seemingly disorganized cluster of clouds encounters an untapped heat reservoir and explosively deepens into a catastrophic Category 4 or 5 hurricane in less than 48 hours. Rapid intensification is the ultimate nightmare scenario for coastal emergency managers because it completely obliterates the standard timeline for evacuations. The current silence of the Atlantic Basin is not a cancellation of the hurricane season, it is merely a delay, a temporary atmospheric pause that is allowing the ocean to stockpile energy for a potential late-season detonation. This brings us back to the most critical realization about the events unfolding across the globe today. The 115-degree heat baking the plains, the explosive supercells threatening the Midwest in the dark of night, and the terrifyingly quiet, energy-loaded waters of the Atlantic are not isolated weather events. They are perfectly interconnected symptoms of a closed planetary system desperately trying to balance its thermodynamic ledger. The heat dome creates the storms. The oceanic climate patterns suppress the hurricanes, which in turn superheats the water, paving the way for future explosive cyclone development. Every single anomaly is tethered to the next by the strict laws of fluid dynamics. As our orbital satellite networks continue to beam back this data, they reveal a fundamental truth about planetary science. Thermal energy can be temporarily trapped, it can be redirected, and it can be stored, but it can never be destroyed. It will always find a release mechanism, and the longer that energy is contained, the more violent the eventual release becomes. We will continue to monitor the structural integrity of the heat dome, the precise initiation parameters for Sunday's supercell threat, and the exact moment the wind shear over the Atlantic finally begins to falter. Make sure you are subscribed and monitoring our updates because the mechanics of our atmosphere are shifting rapidly, and the true consequences of this stored energy have yet to fully materialize. Keep your eyes on the data, and we will see you in the next alert.